Hello, this is Dr. Brown, and this video we're going to work the problems on the Test 1 practice test review. These would be the kinds of problems you would be expected to work on Test 1. The first problem is to find the limit of this function, and as we've said, very often, the way to find the limit is just simply to plug in to the expression, and that's the case here. So you probably would always try that, and you would plug in 4 squared plus 4 times 4 plus 4 is equal to the square root of 16 plus 16 plus 4 equals the square root of 36, which is 6, and the answer is 6. Here we want to find the average rate of change of the function over the given interval. Here the interval is from 5 to 6. The average rate of change is equal to y2 minus y1 divided by x2 minus x1. And I think you see that x2 is equal to 6. And x1 is equal to 5. So let's do the calculation. Y2 is equal to minus 3 times 6 squared minus 6 equal minus 3 times 36 minus 6 equal minus 114. Y1 is equal to minus 3 times 5 squared minus 5 is equal to minus 3 times 25 minus 5. 3 times 25 is 75. Minus 75 minus 5 is equal to minus 80. And so we can calculate the average rate of change is going to be minus 114 minus 80 divided by x2 minus x1, which is 6 minus 5. And so this is going to be minus 34 if you do the math, divided by 1 equal minus 34. So the average rate of change is minus 34. Next problem is find the limit again of another expression. If you plug in x equal 2, you'll get 0 over 0, which is undefined. So you need to find a strategy to simplify the function and look at it so that you can calculate the limit. In this case, we'll calculate the limit as x approaches 2, and we're going to look at the possibility of factoring the numerator and denominator and find a common factor that we can cancel out. So we get x plus 2 times x minus 2 divided by x minus 4 times x minus 2. Be sure you factor correctly, and notice the x minus 2 factors cancel out, and that removes the problem with 0 over 0. And now it's equal to the limit as x approaches 2 of x plus 2 over x minus 4. So this is equal to 4 over minus 2 equal minus 2. So the answer is the limit is equal to minus 2. Now, here we have a graph, shows a number of deaths in the country from certain diseases from 89 to 98. And we want to estimate the average rate of change in deaths from this disease from 1991 to 1996. So we want to look first at 1991 to 1996. It looks like in 1991 had about 1,700. In 1996, we had about 1,200. The average rate of change is going to be alpha at 96. That's the last point we're concerned about, minus the first point of the interval, alpha at 91, divided by 96 minus 91. Alpha at 96, we estimate it being 1,200. Alpha at 91 is 1,700. And then 96 minus 91 is 5. And we calculate minus 500 over 5 equal minus 100 deaths per year. So that answer is D. Now we want to graph this rational function and having our answer the asymptotes, or graph the asymptotes. We're going to put this in our calculator. So I'll bring up the calculator. And it's really great to be able to use a calculator on these tests, because you can get a much more accurate graph more easily, especially if you put it in your calculator correctly, using parentheses. So we're going to put the function in the calculator. It's x squared plus 9 divided by x. And in this particular case, I'm going to zoom to the standard window. Zoom the standard window, and we see the graph, and it's pretty obvious it's going to be answer B. If you wanted to adjust the window to exactly what you see on the answer, go to minus 20 to plus 20 for the window for x min and x max. Go to minus 20 to plus 20 for our y min and y max, and then graph it. Still the same graph, just covering more range here. And it's obviously answer B. Next, we want to find the limit of a rational function as x approaches 4 from the left. In order to do this, we need to draw a graph of the function and then look at it from the left as x approaches 4 from the left. You can go ahead and factor the denominator so you can sort of see what the vertical asymptotes are going to be. Notice that x equal 4, x equal minus 4 are going to be the vertical asymptotes. And putting this in the calculator, we don't have to put the factors in the calculator. We could just go ahead and put it in just like it's given. 3 divided by parentheses x squared minus 16. And let's go to the standard window, zoom 6, and we see the graph, the vertical asymptotes at minus 4 and plus 4 as x approaches 4 from the left. Notice that it's going to minus infinity. So the limit is minus infinity. Here we want to graph the rational function and include the graphs and equation of the asymptotes. So we're going to put this in our calculator, but we're going to first look at the asymptotes. Factoring the denominator, we get 2 minus x times 2 plus x. So the vertical asymptotes are x equal 2 and x equal minus 2. The horizontal asymptotes are, we want the limit as x approaches infinity of f of x. In this case, the numerator is dominated by 2x squared, obviously, because that's the only term. And the denominator is dominated by minus x squared. And that equals minus 2. So y equal minus 2 is a horizontal asymptote. Notice in this case, if one of these answers is correct, you can go ahead and see it's going to be B, because it's got x equal minus 2, x equal plus 2 for the vertical asymptotes, and y equal minus 2 for the horizontal. But we're going to go ahead and graph this, because I would say that everybody needs to look at things from different ways and make sure and check your work. So let's put this in our calculator. 2x squared divided by, remember to use parentheses or you'll get the wrong answer, 4 minus x squared. And let's zoom to the standard window. And sure enough, there is a graph exactly what we thought it was going to be, answer B. Next, we want to find the limit of this expression as x goes to infinity. Well, this is going to be fairly simple. It's going to be 3 over 4 minus the limit as x approaches infinity 1 over x squared. Now notice 1 over x squared goes to 0 as x goes to infinity. So the limit is going to be 3 over 4, which is answer B. Next one's very simple. You want to find the limit of this rational expression. It's really one polynomial divided by the other polynomial. 2x plus 1 is dominated by 2x as x goes to infinity. 9x minus 7 is dominated by 9x. So this is equal to 2/9 is the limit. So the answer is 2/9. Now we want to use this graph to evaluate the limit of f of x as x approaches 0. Always take a very close look at the graph to see what it says. First of all, it says that at x equals 0, the function is defined as 2. It's not minus 2. So this means there's a hole in the graph there. And so the point 0 and minus 2 is not on the graph. I think you guys have learned that. But the point 0 and 2 is on the graph. Now let's look at the limits from the left and the right. The limit as x approaches 0 from the right is equal to 2. The limit as x approaches 0 from the left, just sort of look at the graph, home in on x equal 0, and you notice that you get closer and closer to x equals 0. It gets closer and closer. Y gets closer and closer to minus 2. So the limit from the left is minus 2. The limit from the right is 2. Since they don't agree, the limit does not exist. Now, number 11, we want to find the limit of f of x as x approaches 0. Notice f of 0 is equal to 0. However, the limit of f of x as x approaches 0 from the right, look at the graph as you come down, zoom in on the graph towards x equal 0, and you'll see that y is getting closer and closer to minus 2. And if you take the limit as x approaches 0 from the left of f of x, coming down, as x gets closer and closer to 0, y gets closer and closer to minus 2. And so they agree. Then the limit does exist, even though the function at x equals 0 is equal to 0. But the limit of f of x as x approaches 0 is equal to minus 2. So sometimes the limit is not equal to the value of the function at that point. Okay, explain why the limit of this function does not exist. First of all, the function is f of x equal to x over the absolute value of x. And I'm sure you have seen this function before. For x positive, the function x over absolute value of x is equal to 1. For x negative, the value is equal to minus 1. And these points are not on the graph at x equals 0. F of 0 is undefined. As x approaches 0 from the left, the function approaches minus 1. And if it approaches 0 from the right, the function approaches 1. The answer to this is there is no single number L that the function values all get arbitrarily close to as x approaches 0. The limit from the left and from the right do not agree, and therefore the limit does not exist. Now, here is a question where you have to think about some of the concepts of limits that we've been talking about in the videos. Suppose that a function f of x is defined for all real values of x on the closed interval minus 1 to 1. Can anything be said about the existence of the limit of f of x as x approaches 0? So we just sort of need to think about this. If I have a function f of x that's defined between minus 1 and plus 1, I could have a very well-behaved function that's continuous, and it's defined everywhere between minus 1 and plus 1. And the limit as x approaches 0 of this function, call this f1, would be exactly this point I'm pointing at. However, you've seen a lot of functions that are defined at every point, but there could be discontinuities. Suppose this is f2. Notice there can be jumps in the function at some point. In fact, there could be multiple jumps. F2 is defined everywhere, but the limit from the left, which is that number, and the limit from the right, which is that number, are different. So the limit does not exist. What is the reason? Nothing can be said about the existence of the limit, even though the function is defined at every point in the interval minus 1 to 1. There may be a jump or an oscillation at x equals 0. You can't, one of the other answers is that at x equals 0, f of x must have a limit because it's defined at every point in the interval. But well, we just saw this second case here for f2 that it's defined everywhere, but it has a jump and the limit doesn't exist. So the answer is B here. Notice answer C is that the limit does not exist because it's likely that the function oscillates or jumps. Well, nothing was said up here in the question about possibly there is a jump or an oscillation. It just says the limit was defined at every point, or the function was defined at every point. Number 14, we want to evaluate the limit. This function as x approaches 1. This is one of the easy ones. Always try to plug in unless something weird is happening. In this case, we're just going to plug in 2, 1 cubed minus 2, x 1 squared plus 4 times 1 plus 2 equals 2 minus 2 plus 4 plus 2 equals 6. So the limit is 6. Number 16, sometimes we can do a table of a function. If we want to find the limit of a function is, say, in this case, theta approaches 0. By the way, this should be f of theta instead of f of x, because the variable is theta. As theta approaches 0, we want to try to estimate what the limit is. And one technique for doing this, obviously you plug in theta equals 0 and you get 1 over 0, which is undefined. This particular case, though, what we would like to do is put in values of theta that are close to 0, like starting at 0.1 or minus 0.1 and getting closer and closer to 0 from the left and the right. Notice that if you fill in this table, you get that the limit as theta approaches 0 from the left looks like it's about minus 1,000. Notice you get closer and closer, you're almost at minus 1,000. The limit as theta approaches 0 from the right, however, it's like 999.99. Get closer and closer, it gets closer and closer to 1,000. You could also put this in your calculator and you would see numbers like this, and you would say the limit from the left and the right do not agree, and therefore the limit does not exist. Number 16's got several parts here. It's a very simple graph. Notice this function is not defined. At x equals 3. It's defined for x less than 3 and more than 3. And notice it's not continuous. And we're asked to answer some questions here. The limit of f of x as x approaches 3 from the right. Hop up here on the graph, get closer and closer to x equals 3. Looks like it's getting very close to y equal 2.5. So the limit is 2.5 from the right. If you hop up on the graph, get closer and closer to x equal 3 from the left, looks like the limit is 1. Okay? So those limits do exist, but they're not equal to one another. So the limit, in a minute, we'll see the limit as x approaches 3 does not exist because they don't agree. Now, the next part of the question. Does the limit of f of x as x approaches 3 exists? And the answer is no, because the limit from the left and the right are not equal. And notice the answer D saying no, that it does not exist because f of 3 is undefined. Having f at 3 to be defined is not a requirement for having a limit or not having a limit. What you have to do is look carefully at the graph and decide whether the left hand and the right hand limits agree. Now, we're looking at another value of x that's being approached. Here we're talking about 4, x equals 4. Looking at this function as f of x, as x approaches 4 from the right, it looks like the limit is 3. And approaching from the left, the limit is 3. And number 16, the last part, is does limit f of x as x approaches 4 exist? If so, what is it? If not, what not? No, why not? The answer is yes, it does exist, and it equals 3. Number 7 is one of those, if you plug it in, x equals 9, you get 0 over 0. So we have to use some technique for simplifying the expression. This particular case, when you have a radical minus a number, it's probably a good case in which you want to take the radical conjugate and multiply it, the numerator and the denominator, and see if you get some simplification. So let's take this limit of x minus 9 divided by the square root of x plus 7 minus 4 as x approaches 9. And now we're going to multiply the numerator by the square root of x plus 7 plus 4. We call that the radical conjugate. And the denominator, we're going to multiply by the same thing. That way we don't really change the function. And now we need to see if we can simplify things. This is going to equal the limit as x approaches 9. And I'm going to just write down the numerator as is right now until we see if we get some simplification of the denominator. Now we need to FOIL the denominator. It's going to be the square root of x plus 7 times the square root of x plus 7, which is x plus 7. And now you can see that the outside is 4 times the radical, and the inside is minus 4 times the radical, so they cancel out. Then the last is going to be minus 16. And this is going to be the limit as x approaches 9 of x minus 9, the square root of x plus 7 plus 4, divided by the numerator is going to be x minus 9. And notice we get some relief here. We get rid of the problem with x equal 9 and cancel out the factors here. And so calculating this limit, we get the square root of 9 plus 7 plus 4 equal the square root of 16 plus 4, which is equal to 4 plus 4 is equal to 8. So the limit is 8. Now, a lot of the problems here are just looking carefully at the graph and seeing if there are any holes or jumps or discontinuities or whatever. Here we're just asked, find all the points where the function is discontinuous. In this particular case, it's discontinuous at the hole here, where f of 6 is not defined. Okay. The answer is x equals 6. It's a point where the function is discontinuous. If the graph had looked like this, with no holes, you would have said there are no points where it's discontinuous. So look for holes and look for jumps. Next problem, you just need to look at everything carefully. It's pretty obvious there are 2 holes at x equal minus 2 and plus 2. So that's where it's discontinuous. If we had taken those holes out and had just this would have been a completely continuous function. But in this case, with the holes, the answer is x equal minus 2 and x equal plus 2. Now we have a function x defined below and defined on the right. We have it graphed below and defined here on the right. And we have a nice little neat graph. The question is, does the limit of f of x exist as x approaches 0? Well, if we look in this area here, everything is nice, hunky-dory. Coming in from the left, it approaches 0. Coming in from the right, it approaches 0. So we would say the limit of f of x as x approaches 0 is equal to 0. So the answer is yes. Number 21, to what new value should f of t be changed to remove the discontinuity? Notice that we need to draw a graph of the function to really get an idea of what this looks like. If we just very simply draw a little scale here. For x less than 2, the function is 2x minus 4. So at x equals 0, we're minus 4. And it's a straight line all the way up to x equal 2, but not including 2. And the equation is 2x minus 4. Now, to the right of x equal 2, the slope is 1. So the function is y equal x minus 2. The value of the function at x equal 2 is said to be 2. So there is a discontinuity here. And there's a hole at 2 and 0. In other words, 2 and 0 is not on the graph. However, if we want to find the new value of f of 2, what it should be, to remove the discontinuity, we would let f at 2 not be 2, but 0, and then that would remove the discontinuity. continuity. So the answer is 0. Number 22, we want to find the slope of the curve at the given point P and find an equation of the tangent line at P. Well, we're going to do this problem two ways. We're going to do it using the definition of the derivative. Now, the derivative at a point gives us the slope of the curve at that point. And we're just going to use the definition f prime of x equals the limit as h approaches 0 of f of x plus h divided by h if the limit exists. In this particular case, we're going to get x plus h squared plus 5 times x plus h, because we're plugging in x plus h for every value of x that we see. So this is f of x plus h minus f of x. F of x is x squared plus 5x. All divided by h. And let me put the limit here in. Limit as h approaches 0. So we want to calculate this limit, and continuing, we get x squared plus 2xh plus h squared. That's x plus h quantity squared, plus this term is 5x plus 5h and the last term is minus x squared minus 5x, and we want to divide by h, and we want the limit as h approaches 0. So let's calculate this. Notice the x squared and the minus x squared cancels out. The plus 5x and the minus 5x cancel out, and we get the limit as h approaches 0 of, by the way, this is 2xh, the cross term. So we get the limit of 2xh plus h squared plus 5h, all divided by h. And f prime of x then is equal to the limit as h approaches 0. Notice we've got a common factor h in the numerator, which I'm going to take out. We're left with 2x plus h plus 5 divided by h. Notice the h cancels out, and that relieves us of the problem of h going to 0. And taking the limit now, plugging in h equals 0, we get 2x plus 5. So that is equal to f prime of x. That is the derivative of the function. The slope at x equal 4 is f prime of 4 is equal to 2 times 4 plus 5 equals 13. So the slope is equal to 13. And the equation of the tangent line is y equal 13x plus b. And we need to find out what b is to make it go through the point 4 and 36. So y is equal to 36, x equals 4. Plug that in and we get 36 equal 13 times 4 plus 6 plus b. And b is equal to 36 minus 52. By the way, 52 is equal to 13 times 4. So b is equal to minus 16. So the equation of the tangent line is y equal to 13x minus 16. And as we said, the slope is 13. Now, we've already talked about and hinted at what the derivative of a polynomial is. A really simple way to work this is to look forward to the derivative being y prime if y equals x squared plus 5x, then y prime is equal to 2 times x to the 2 minus 1 plus 5. So the derivative is 2x plus 5, which is what we got here, but look at all the work we had to go through to do it. And then we quickly know that y prime at x equals 4 is equal to 2 times 4 plus 5 equals 13. So I'm very happy to say that in the future we'll be doing, in fact, you can actually do it on the quiz if you can remember how to take the derivative of a polynomial, if we had one that's a polynomial. So that's the answer. There's a long way and then there's a short way. Number 23, graph a rational function. Include the graphs and equation of the asymptotes. First of all, for vertical asymptotes, there are no factors in the denominator. So there's no value of x that in the denominator that will make it 0. To find the horizontal asymptote, we take the limit f of x as x approaches infinity. Numerator is the numerator is dominated by x, and the denominator is dominated by x squared. So the limit is x approaches infinity. X over x squared is 1 over x, so it's the limit of 1 over x as x approaches infinity equals 0. So the horizontal asymptote is y equals 0. Now go ahead and put this in your calculator. Tell you the truth, you can just about do it in your head. Very carefully put it in your calculator. X divided by, now use parentheses, x squared plus x plus 4. Let's zoom to the standard window. And looks like it's going to be answer A. Yeah, going to be answer A. To make it look a little more, change the y min to minus 4, y max to plus 4. You'll be able to see it just a little bit better. And it's obviously answer A. And you see the y horizontal asymptote being y equals 0. So answer 23 is A. Number 24, you're given the graph of a car's position versus time, and we want to answer the following questions. At which point is the car's velocity the greatest? Which point is the car going backwards at the highest velocity? And at which point is the car stopped and also closest to the starting point? Well, we are given S equal position. We know that the first derivative of position is equal to the velocity. And to calculate the velocity, we need to know the slope of the tangent line, or actually do an approximation. So if I want to look at point A, I would put in a tangent line that looks about like that. At point E, I would put in a tangent line that looks about like that. And at point C, tangent line would be horizontal as it would be at point D. And let's just do a red tangent line for point B. Would look like this. So now to look at this, the slope at A is greater than the slope at E. So it's going fastest at point A. At point B, it's going backwards at the largest negative velocity. And at point C and D, the velocity is 0, it stopped, but the point that's closest to the starting point is D, so the answer is D for the last part. Now, we have a gigantic planet, Cyclops, far, far away. The distance an object falls after being dropped is given by S equal 80t squared. Notice on Earth, S would be 16t squared. T is the time in seconds after the object is dropped, and S is the distance in feet. We want to find the average rate of change of the object's position over the interval 0 to 2. So the average rate of change is going to be S of 2 minus S of 0 over 2 minus 0, which is 80 times 2 squared minus 0 over 2 equals 320 divided by 2 equal 160. So the average rate of change is 160. Now on the test, I could possibly turn this around and ask you to find out what is the velocity instantaneously at t equal 2. In this case, you would have to calculate the derivative, in which case the derivative would be 160t, and the velocity, in other words, the velocity is equal to S prime. The velocity at 2 would be 160 times 2 equal 320 feet per second. So the instantaneous velocity is 320 feet per second at t equal 2. The average velocity from 0 to 2 was 160. Last problem is another radical problem. And we're going to have to use a radical conjugate. Here we would say that's the limit as x approaches minus 11 of 10 minus the square root of x squared minus 21. Divided by x plus 11. And we want to multiply the numerator and the denominator by the radical conjugate, which would be 10 plus the square root of x squared minus 21, and multiply the denominator by the same radical conjugate. And now let's see if we can simplify this. This equals the limit as x approaches minus 11. FOIL out the top and you get 100. The outside is 10 times the radical. The inside is minus 10 times the radical, so they cancel each other out. And then you'll have minus the radical times the radical, which is the number under the radical itself. And just write the denominator as is until you simplify the numerator. And this is equal to the limit. X approaches minus 11. And this will become 121 minus x squared over x plus 11. 10 plus the square root of x squared minus 21. And we're going to factor the numerator into 11 plus x. 11 minus x. And this is x plus 11 or 11 plus x. And 10 plus the square root of x squared minus 21. Notice 11 plus x cancels with 11 plus x. And now we can just simply plug in x equal minus 11 and get 11 minus 11 divided by 10 plus the square root, plugging in minus 11. We get 121 minus 21. Simplifying, we get 22 over 10 plus the square root of 100, which is 22 over 20 equal 11 tenths. So the answer is 11 tenths. And that is the review for test 1. Good luck to everybody.